Okay, it's now time to start. So it's 11:50. So go back to the. So this is IPSECME working group, the last best session in this IETF. And for us, because we have a lunch and cookies and so on, so this is always best. Always come to there. All right, so I'm Tero Kivinen and
David Waltermeyer.
And we are our chairs. And then if you go to the next slide, so here's the note. Well, you probably have seen it already. If you haven't, then you probably need to go and visit a couple of more sessions during the week. So the next one. So I put the blue slide. Okay. Blue sheets going forward. Then we need some volunteers. We have already one note taker. I think where he is. There. Anybody else who wants to just take it? Yes.
All right, I can go eat.
Okay, good. Yeah, that's actually very good to if you are making. Let's put it. When you are making comments in the mic, it's very good to go and check out that your comments are actually accurate, represented in Etherpad, and fill in your name or something like that if you don't. And do we have a chapter scribe? Okay, thank you. I'm also trying to follow it also, but I mean it's good to go. All right, go to the next slide then. In wrong window. All right, so here we have a quite full agenda, and we try to keep it, which means that we are going to be cutting people off if they are taking too long time. So, anybody has any bashing for the agenda? No, then I think we move to the rechartering 3 minutes ahead of time. Okay, you take that one.
Yeah, I can do this. Okay, so we've made some progress on some drafts. We've got the DSA draft in the RFC editor queue. I think it's waiting on some IANA related things, so it should be progressing pretty soon. I requested publication of split DNS. I think we're waiting for AD go ahead on that draft. At this point, so welcome. Okay, so maybe we can ping him after the meeting on that. We also have a couple of other drafts that are, I think, getting pretty close to working group last call. I did send an email out about implicit IV. We adopted it at the last meeting in November. There's been no comments on the draft since then. So if there are no concerns, I'd like to put it up for working group last call as a way to generate comments on the draft. Great. We won't progress it, though, unless we do get some feedback during the working group last call. Can I see a quick show of hands for folks that are willing to review this draft? Okay, so about 5 or 6 or 7, maybe. Great, thank you. And then we've been working on a bunch of new charter items. Thank you all for your comments on email. Do you want to speak to that?
All right, yes. So if you go actually forward, I think the next slide is this is the current milestones. And we have put, as you see, we have almost completed all of them. And we have a couple of those that are very soon should be able. So if you can take the new slide set I made just a few seconds ago, the new milestones. No, not that one.
Let's see the...
Where's it?
Is there one that says milestones?
I think it's the last one, probably that one. Yes. All right. Cool. So these are the new milestones that are going to be, we are up. I think about these. So this wasn't shown before because we actually picked them up like a couple of minutes ago. And and we have the other items that are, we send it to the AD said that, okay, he made some changes, some small text changes he's going to be putting the charter forward. So I think we are going to get in a charter very soon. All right, so that was this discussion about the charter stuff, and we didn't. If we go to the next slide on there, we didn't add the responder mobile or privacy concerns because there was so much discussion about going on, and we can add them later if we need to be. But I think we need to be having more discussion before we add them to the charter. We did add the address failure errors and the labeled IPsec. I actually have some concerns now about the labeled IPsec because I think the current method isn't good, but we can discuss that when we have a charter item. But anyway, that's good. Okay, then we go to we already actually went through the draft status, but then we have the Valerie's comment about or presentation about the QR IC version 2 draft. So, there. Yes. Valerie.
Well, hello, I'm Valery Smyslov. I will make a quick status update of quantum resistor IQ2. Next, please. So from 0.0 versions that were presented in Singapore, we have the following changes. First, I think the most important change is SCAP PI, SCAP PI, and SCAD is changed from using PRF to PRF plus to accommodate possible use cases when key size of PRF is not equal to its output size. Currently, there are no such PRF defines, but it is quite possible. It is not disallowed. So it's the most important change because it changes bits on the wire, but it's easy to accommodate in the code. Well, we add a clarification on using PPK in case of IP authentication. So it is only used in the last ICAOS flight when aus preload are exchanged. And in this flight, PPK ID is included also. And it added clarification that PPK is used only in initial IKSA setup and not in any subsequent rekey or assumption of the same IKSA. Well, added notification that initiator must ignore content of PPK identity if for some reason it is not empty. The draft requires that it is empty for responder, but who knows? So receiver must ignore it. We rename PPK support to use PPK because it to better reflect its purpose. And we added official code points that were assigned from IANA and some minor editorial changes. Next slide. Next. Well, so at least 4 vendors have running code implemented the latest version of the draft, and we perform interoperability testing. It's almost full metrics, and everything goes smoothly, more or less. So we're interoperable with each other, and we believe the document is ready for workgroup plus call. So that is it. I think one issue is the document is marked in data tracker as informational, but I remember that I recall that it was a consensus that it must be standard stack, so it just must be fixed.
Okay, we'll update the status. Thank you.
Thank you. Any question?
So the only thing is that this document actually implements 2 things. One is a extended negotiation for which authentication method to use, and one is doing the PPK. And so I found in one of our use cases that if you have a whole network using one kind of authentication and you don't want to switch and you can't upgrade your network all at once, you want to actually have some sort of negotiation on the which authentication mechanism to use. So we ended up using basically with a private use number the exact same mechanism used in the PPK draft for our own, auth null to certificate authentication. So the only question I guess for the group I have is, should we somehow make this more generic? So the notify that's now sent is specifically for the no PPK auth. Should we have one that's more generic with a subtype that says this is for authentication method X? In case you want to use that, I'm okay with that too. And so I know it's late for this document, so I'm also not sure if I want to change this document. But I do think there's some use of having this more generic mechanism that's not related only to the PPK draft.
as far as I understand, it's a question to the group, not from me. Well, but still, I will express my opinion if possible. Well, I think that it is a good thing to have some method to not negotiate, but at least to announce authentication method capabilities from each side. But I don't think this particular method that you use in this draft is the best one. Well, I think that probably some, well, it uses some no PPK else notification that offers two ways to authenticate, but it doesn't scale well. So I think that it's better to invent something that each side can announce its supported authentication method in the IKSA need or somewhere before the actual authentication take place, and doesn't calculate twice an authentication information. So this method particular is for this draft because there are some peculiarities with PPK that prevent it using more generic methods. That's my opinion.
Tommy Pauly, Apple. So we were some of the people who were doing the interop testing, and originally we had been doing interop testing with Paul's implementation on an earlier version of the draft, and we updated it. And so one of the diffs in there was the no PPK auth. And that's the area that, like, in our implementation, reading through it, I was a little bit confusing at first how that worked. So I think I am kind of attracted to the idea about being more flexible in the future, but either way, I would like to see maybe just some of the text around no PPK auth be elaborated on, expanded upon, to make it really clear that this is what you're doing. It's kind of just in the text there, it just looks like a normal notification, but it actually has a whole bunch of others. Like, it essentially is another auth payload. It's much more like an auth payload than it is like a notification payload. It kind of does briefly describe what goes in there, but maybe even just like a very simple bit format diagram would be useful, because technically in the auth payload you do have another byte, I think 1 byte there for like the type at the beginning. This is not present there. You do say it is the auth data that would normally go in the auth payload, but it may be useful to also specify, and that's not the full auth payload, that's just the latter portion. So maybe just drawing that out to be really clear would help people as they're implementing this.
Can you please provide the text that you think is suitable?
Sure. I can provide text. But if you agree that that's a good approach.
All right, thank you. So now we're into the...
So now next we move to the other items then. So these are actually, all of these are, or most of these are the new charter items, so they are not yet in the charter, but should be soon. So we start with the post-quantum key exchange stuff for IKE version 2.
Okay, next slide, please. Right, so I thought I should give a very sort of a brief agenda on what I plan to do here. So quickly recap on what we've done on version 0, and then there was some feedback we got from version 0. We then went back drawing board to look at the design criteria. From the design criteria, then we wrote version 0.1. And most importantly, for the purpose of this thing, is that we'd like to get the input from the working group on some of the questions that we can ask later, because we do need input from you on the direction where we should go going forward. Right, next, please. So quick recap. So problem statement, basically, we want to have a way to exchange, not in addition to Diffie-Hellman public data, but also post-quantum public data. And we want to do it in hybrid mode, just like shown in the diagram there. So we want to do it in parallel. And then on a version 0.0, the way we do that is we introduce a new transform type. As you know, that transform type 4 is for Diffie-Hellman group, and we introduce a new transform type to carry the post-quantum public data. And also, we introduce a new payload type to carry the actual public data. And then, obviously, post-quantum public data is pretty large. Some of them is more than 1 kilobyte. So we will end up with a fragmentation problem. So at that time, we decided, okay, right, there was a draft on TCP encapsulation. We will use TCP encapsulations. And then, you know, in IETF 99, we got feedback, that's not a good idea. I mean, we still need to use UDP. So, all right, okay. So we took that into account, right? And also, there was a strong sort of an input, say, hey, you can't just simply introduce new transform type. There could be interoperability issues. All right, that's good. So we got that feedback. Next slide, please. So then we, all right, went back to the drawing board, and then we say, okay, what are the main criteria for our design? And these are the things that we thought that are not all of them, but these are the main ones. So the first one, obviously, is that the need for post-quantum key exchange, or the need to perform this, to include post-quantum cryptographies into IETF2. And the second one is hybrid mode. So obviously, if we replace the current working sort of a Diffie-Hellman ECDSA with something that is not known, it's a bad idea. So we want to do it in parallel. We want to, at least in the transition period, we do not want to weaken the security. So we want to use the Diffie-Hellman key exchange in conjunction with post-quantum key exchange, right? And the third item is the focus really is on confidentiality, meaning that we imagine the case that where there is a passive attack, there are people capturing data and wait for the time when there are powerful enough computer to decrypt it. So we want to protect against that kind of attack. Whereas there is also another kind of attack, which is active attack, where people can do live man-in-the-middle sort of attack on the line. That would only be a problem when there is quantum computer. Obviously, as far as I know, there is none at the moment. I could be wrong, but right. So the focus here is on confidentiality. And number 4 is we want to limit the amount of data exchange, meaning here is that the post-quantum public keys are pretty large. We do not want to send too many of them on the line. We only want to send when we know the peer, okay, we agree on this type, and that's it. We want to exchange that data. Future proof, point number 5. So we say that, okay, we should not delve into the crypto in detail, right? We should treat things as a blob. So let people like NIST decide what algorithm it is, but what we want to do here, we want to create a framework such that it's very easy. Let's say in the future, there's a new algorithm, we can slot it in without changing the framework on how we exchange the public data, right? And number 6, efficient way of negotiating hybrid algorithms. So on our earlier draft 0.0, we only say that, okay, we will exchange one Diffie-Hellman group one Diffie-Hellman public data and one post-quantum public data. But talking to a number of people, there seems to be a need to exchange multiple of these post-quantum public data. So we need a way of efficiently encoding this information such that we will not end up with an exponential, list of data to be exchanged. Number 7, obviously, I talk about that. Obviously, fragmentations need to be resolved rather than relying on TCP, right? And then number 8, which is very important, is backward compatibility and interoperability. And lastly, FIPS compliant. This is, sort of related to point number 2. Basically, from what I understand, is that if your equipment is FIPS compliant with Diffie-Hellman, if you add if you do another key exchange, post-quantum key exchange in conjunction, we are not breaking that FIPS compliant. Right, so that is the design criteria. Next slide. Okay, backward compatibility. So one of the things that we learned was that introducing a new transform type is going to create problems, especially because having 12 years since we've got IETF2, there's no new transform type. Yes, in RFC 1726, it says that a new transform type should be ignored if the peer doesn't understand that. But from what we tested, that doesn't seem to be that true, unfortunately. So then we thought, okay, so we need a way of exchanging this information, and we need to meet the following point. Basically, if we try to do something that does not introduce new transform type, no new payload type unless the other side supports it. And but on the other hand, if you look at notification payload, it's okay to introduce new notification payload. So based on this point, next slide, please. So we try to sort of see how we can do that. So we came up with this sort of this two-phase exchange where instead of using new transform type, we create a new Diffie-Hellman group using some number that has not been used before, and that group denotes sort of a hybrid sort of a type. And we exchange it in the first round, ISA sort of a message on the first round, and if the other side understands that, then it'll send sort of if the other side doesn't understand, it'll say, okay, invalid KE payload and so on and so forth. And if it understands, then you can go on the second round where we will use sort of I'll come to that later, send sort of the post-quantum public data in multiple KE payloads. So in this case, there's no need to use a new transform type. Next slide, please. Okay, fragmentation, right? This is one of the very difficult tasks on this thing. So fragmentation obviously is supported in IETF Valerie, obviously he's got that draft on there, but unfortunately that sort of happens on IOTH onwards. And here we're trying to do the exchange on the ISA init message. Obviously, we thought that, okay, one of the aims here, obviously, we try to keep sort of the message flow, unchanged from the standard sort of V2 transport. So one idea that we've got was that, okay, we could actually introduce this a frag pointer, which is basically a fragmentation pointer, which you slot into the current sort of a KE payload that is too large, and the actual body is split into one or more of this frag body.
Yavnir, so when you say it's large, how large?
Well, some of the KE payload in general will be 1 kilobyte or more. So okay. So if you exchange more than one of that, for example, then there could be problem with fragmentations.
So we're not getting into trouble with the payload length field that's only 16 bits.
Well, the payload length bit, it's obviously 16-bit. The most you get is 64 kilobytes. So
so we're not in trouble with that.
Actually,
no.
The payload length is 32 bits. The UDP size is 16 bits.
Payload length field?
Oh, payload length, yeah. But actually, the message length for IKE packets is 32.
Yes.
Yes.
Tommy Pauly. So just a clarifying question on the concerns here. So on the last slide, you mentioned that you're proposing two different exchanges. Like first, we would do an exchange that would say, I support this new group. And then there would be some further exchange that would do the equivalent KE, but for quantum safe keys. And then you're also talking about here, fragmentation, the fact that you can only do fragmentation on auth. What message type are you imagining to use for this second exchange? Because technically, my impression is that the fragmentation really is not more about auth. It's just that it has to be after the initial IKSA init.
Yes.
So I don't know exactly what you're proposing that second message to be. Is it another init or is it an auth or something? But it could theoretically use fragmentation as well because we've already done one exchange.
Actually, I was we have another presentation of fragmentation later. But actually, if you go back one slide, one of the things actually was saying you're saying that you are using two different key exchange payload in the same packet, and that's actually something that is most likely going to be causing trouble. No, you are actually planning to have a separate. First round and second round, but both of them are using key exchange payloads.
Yes. So.
Okay. Yeah.
On this one, we sort of check. Do you support that? If you support, then we go here.
Yeah. Okay. So there, but actually, if you already know that at that point that you, in your previous slide you said that when you know that you are supporting it, you can also use the different payload types, and so I think actually it would be better to have not to overlap the key exchange type, but actually key exchange payload, but use a separate. Especially as I see, we might end up having more than 64 kilobytes of that.
You're saying that new payload type here for carry. Okay.
And similarly, if your KE payload is wrong, you have to restart from scratch. So you're taking another round trip hit. So if a post-quantum capable machine connects to a non-post-quantum capable machine, then you're going to have this additional hit, right? So it would be nicer if it's Magnus where you don't have to do that. So if in the first init packet you can have somehow these two separate KE payloads, and then if the other end doesn't support it and they can ignore that payload, they don't take the extra round trip hit.
One of the things that we tried as well is that in some of the current implementation, and again, what we've tried was that sending sort of a packet, a new payload type to appear, and unfortunately some of the peer does not behave as what we want. So it should sort of ignore it. But some cases we found that it replied with an invalid syntax, for example. Well, I mean, yes, I do agree. In ideal world, I think we would like to fix all of them, but it's like we don't know if all of them could be, rolled out. So, and again, this is sort of the input we will need to get from the working group if that is the direction we should go. Yeah, I mean. Yeah.
So, Yavnir, I'd like to push back on Paul's suggestion. I mean, we could have done that with KE payloads for all the regular groups that we support, and we chose not to do that to make the protocol more simple and at the cost of the occasional multiple round trips. But I don't think this introduces anything fundamentally different from, say, Curve 25519. Just yet another KE method.
Okay, so, oh, sorry, yeah, I've got something here, sorry. Very quickly, obviously, one of the issues was downgrade prevention. So we know in the normal IETF, we need to send a full set of a proposal. So on this sort of exchange, on the second exchange, we do the same thing. Obviously, on the first round, we use the KE payload to do that. Obviously, we can't do that on the second round. So what we proposed was to use notification sort of a type to carry the full proposals. And there are a number of ways to detect these things. Obviously, one, we don't sort of mandate that, but one could use state allocations or use sort of rely on IAuth to detect any changes, or one can use cookie, which actually we thought would be a recommended approach. Right. Next one, please. Okay, so I'm gonna do. We would like to get question basically from the working group if this sort of design criteria was okay, and if we miss anything, or is anything that is simply incorrect here. But before I do that, I would like to flip to the next slide, the last one. Now I put this slide, and I didn't know that Valerie is gonna do a talk on that one, right? So this is another way of how one can do sort of the exchange. So it will be grateful once Valerie has done the talk. We will get sort of a more input from the working group on which directions our draft should go. We could use this, or we could use the frat pointer or frat bodies. It'll be good to get sort of more clarity on that. So back to this slide. Right. So any sort of input on this design criteria, or anything we have missed, or anything that should be changed or added?
Marko Żuchowski, NCSC. Just a comment on the negotiation of the hybrid algorithms and the way you're doing it in the draft at the moment. It's pretty flexible the way you do it. I don't think it's arbitrarily flexible for allowing arbitrary combinations of classical and post-quantum algorithms. I think it's sufficient for most purposes. Just wanted to make the observation that it's not entirely arbitrary.
Okay.
Valery Smyslov, LS Plus. Well, I think I'm a principal opponent of your draft, so I just repeat what I wrote to the list. So I think that it is better to use a slightly different approach, especially for fragmentation, for negotiation. Negotiation, I think it's better to reuse transform types. And it is possible to make, I think it is possible to make it workable even in most cases, even if we have some buggy implementation, but I hope the buggy implementation will gone at the time when this draft become this ubiquitous, becomes an RFC, because it's a long-term draft, a long-term solution. So for long-term solution, it is not a good idea to rely on some bug implementations that are all around. And the second point that I think it is better for me, from my opinion, to reuse existing fragmentation mechanism by introducing intermediate exchange and putting all the QSKE stuff there. So that's what my next presentation will be about. And I think that we have some conversation with authors of the draft, and some fruitful, probably. This is the approach that if our group decide it's okay, probably this approach is what should we go.
So I have a question about point 9, the FIPS compliance. And do you actually achieve this? Because you're proposing here a mechanism that includes some NIST-approved algorithms and some algorithms that are still not NIST approved, and they're kind of mixed together. And I'm not sure that passes the checks. Well,
it does. I mean, we got NIST basically state that. I mean,
you do?
Yeah.
Okay.
I can send you the details.
Great.
Yeah.
One of the things you have to think about also is, especially if you are thinking about doing what you're proposing here to create a new Diffie-Hellman algorithm, is that we already have the Diffie-Hellman, invalid key exchange payload, meaning that if we want to, you propose curve 25519, and I don't support that, but you also propose 3000-bit mod P group, we can actually fall back to that, and we want to see how that interaction works. And that's actually, and now if you propose both mod P and quantum plus this, but you have a different algorithm, so it's actually getting very complicated. That's why I was thinking about it might be better to actually, as people were commenting, have a separate transform type there and negotiate them separately, because I mean that allows us to negotiate them separately, because we probably don't want to tie them together. Okay, this quantum algorithm can only be used with curve 25519, and this other quantum algorithm can only be used with 3000-bit mod P, because we don't want to create 10,000 more or tens of more combination of that.
Indeed.
So I think that's why I was thinking about it might be, but that's one of the things we can actually think of later. Yeah.
Thanks.
Sheila Frankel, NIST. I have a question for the group and about the fragmentation approach. And I think it's something that should be addressed by this group and possibly by others. Typically, you're requiring Ike to perform fragment reassembly. And
Yes.
typically fragment reassembly, it could be a vector for all sorts of attacks. So I just want to make sure that however it's done, it doesn't bring, additional possible attacks into Ike.
Yeah, so I can comment on that. It says that in Ike, we try to keep the Ike SA init, the first exchange, so small that it never needs to be fragmented. And the reason for that, so when you receive the first bucket, you can do the cookie exchange to require the other end to show that it has a reachable IP address without storing any state, including the fragmentation state. And after, when you have received the first bucket, after that, we can do fragmentation in IP layer also, because I mean, that's, then you can, in principle, mark your kernel so that, yes, from this IP address, I allow to be doing reassembly for the IP fragments because it's known IP. But that's actually something, and we are all, as an agenda item, we are going to moving Valerie next, skipping Paul, so because his presentation is directly related to the fragmentation issue, and I think it will be better to come back with the fragmentation issue after his presentation.
I will answer the question.
Well, I mean, I appreciate that people may not have an input here, but it would be good if anyone has got an input, send it on the mailing list. We'll be happy to take them into account.
Okay, thank you.
Yep, thank you very much.
So next is then we skip the labeled IPsec and move that to later if we have time, because the slides came late. And then we go to the accelerator exchange for Ike version 2. So this is going to be the fragmentation issue, solving the fragmentation issue.
Hello once again, I'm Valery Smyslov. This draft is inspired by Tero's idea. I need to create a Tero who suggested to include an intermediate exchange between Ike init and Ike auth. Next, please. So what do we have now? So we have two Ike setup is done by performing two exchanges, Ike init and Ike auth. And there are some properties that Ike init messages are usually rather small, so no IP fragmentation takes place. And Ike auth messages can be large because they can transfer certificates, and so IP fragmentation is possible for Ike auth messages. And the IP fragmentation is a bad thing for UDP-based protocols because some middle boxes don't like UDP fragments. So we have RFC 7383 that defines IQ2 fragmentation that allows to avoid IP fragmentation, but it can only be used on Ike auth and later exchanges when we already have key material, because it requires that message to be encrypted. So it can be used in Ike init. Next, please. So the problem we have, some recent development in recent proposals in quantum safe cryptography defines a new key exchange method that have rather large public key payload size, key exchange payload. So in this case, IKSA init messages grow beyond MTU, and this may cause IP fragmentation. That is a bad thing, as we already know. So it is possible to, I think it is possible to add fragmentation support in IKSA init, as previous presentation suggested, for example. But there are some complications. IKSA init messages are unprotected, and so adding fragmentation to unprotected messages may lead to various denial of service attack. For example, reassembly queue poisoning, when attacker who is only able to see and to inject messages can inject bogus fragments and prevent so poisoning reassembling queue and prevent exchange from its completion. Next, please. So proposed solution. Let's add an intermediate exchange between IKSA init and IKAUX. Let's call it IKAUX, auxiliary. And this exchange is protected using key exchanged in IKSA init. So it can be, fragmentation can be used in this exchange. So it put all large payloads that need to be exchanged before IKAUX take place in this exchange. Next, please. So new large payloads are placed in IKAUX. IKAUX messages are encrypted and integrity protected, so standard type fragmentation can be used. They are authenticated by small modification of how payload is calculated in IKAUX by adding ACV of these messages to calculation of the payload. Oh,
sorry, Paul Wouters. So you say they are integrity protected, but they're not.
Sure. Well, why not?
Because you don't know who you're talking to when you're doing
it is not authenticated, but it's integrity protected. I do know that I talk with you. I don't know who you are yet.
No, Yavnir, they're encrypted and identity protected, and as long as you assume that these algorithms are good enough.
Yeah, of course.
As long as you assume that we haven't had the quantum crisis yet.
Well, yeah, I agree. Online.
Yeah, that's the part. Online. Oh, okay. And also, as you have last year saying that they will be authenticated when we finish the actual authentication using IKAUX. So that's so they are encrypted, integrity protected while they are in transit, and then later we authenticate them.
Yes, exactly. Thank you. So next, please. Next, please. So, well, this is just a generic approach. It can be used with multiple use cases, but the obvious use case that inspired all this approach is QSKE, quantum safe key exchange. So it is not limited to QSKE only. Any large payloads that are to be exchanged before IKAUX take place can be placed in IKAUX. But let's talk more about the first application, QSKE. So IKAUX messages are protected using keys derived from key exchange. So key exchange, so IKSA init is the usual IQ2 exchange, and it must have key payload, even in case QSKE. It's a feature it must have. So it must be either classical key exchange, or in case, for example, NIST or somebody else will come with QSKE exchange that have a smaller key size. It is possible to use this exchange in IKSA init, but IKSA init must exchange keys in any case. And all subsequent keys. So, well, but it is powered by QSKE. QSKE requires that we have several quantum safe key exchange because we don't trust any of them. We want to combine. So all the other key exchanges are placed in ICAUX. Keys for ICAUX and for subsequent key exchange are calculated by modifying. So we first calculate a key seed once we complete AKSA need to derive keys that protect ICAUX. And then once ICAUX is complete and we know we get an additional entropy from QSKE exchanges, we perform calculation of new SK seed by standard IQ2 computation of derivation load for rekeying. Next, please. So this is an example, just for you to be probably more for illustrative purposes. First, after first IKSA need, we compute SK seed and compute SK seed from key exchanges, from key exchange that was performed at IKSA need. And this SK seed is used to derive SK E, SK A, and SK D. SK D is used later. SK E and SK A are used to protect ICAUX. And once we complete ICAUX, that exchange quantum safe key exchange payloads, we recompute SK seed to get our final keys that will protect ICAUX, OS, and subsequent exchanges. Next, please. So,
Yaron, Chef, a question to the previous slide. How does the initiate, so if it's the initiator that wants to move from OGS to OS, that's easy, but how does the initiator know that the responder doesn't still want to send more stuff? And so it's good enough to move into ICOS?
Don't understand.
So actually, because these are IQ 2 exchanges, this IQ 2 exchanges, which means we always send a request and reply.
Yeah,
so
sure.
The
Sure.
responder cannot send anything unless we send the request from the other end. And now the question is that if we have multiple ICAUX exchanges, then what happens? Do we actually calculate SK seed for every single step for the next one, or do we do that only
it's
after?
a question. It's a question for cryptography. It's just suggested. Well, ICAUX itself is not tied to QSKE type.
Yeah.
So this particular application is tied to QSKE type. So this is probably a question to Scott or to others. This is just suggested. How we should do it.
Actually, I was thinking about that. I think that in ICAUX, we could probably say that, okay, you can do one ICAUX matches, or you can do multiple, depending on the reason why you are doing them. So if your quantum key exchange requires multiple of those, you decide what you do and negotiate it somehow with the other and do those. And then we probably do only the SKC final, including all the traffic, all the material we have. We don't do every single step because it actually might be so. We might have a three-phase, quantum key.
Both approaches are possible. If you do multiple ICAUX, you can recompute SK seed after each.
Yeah.
Or you can accumulate all the exchanges.
I would propose actually doing it only at the end.
Well, it's 2D. To a group to decide.
Because it might not be Diffie-Hellman type of thing. It might not be request reply. It might be request reply confirm something.
That does not seem to be a issue in practice. I've seen only one key exchange which didn't fall into the Diffie-Hellman key send reply paradigm, and nobody takes that one oddball seriously.
Tommy, so it sounds like, based on the other comments, that we should we specify that from the responder behavior, like with auth. So normally I do init from the initiator, and until I start doing auth, I can't get informational packets. We should also just be very clear in the document that aux is only for being in between init and auth, and the responder is not allowed to initiate its own messages the other direction during
Not
that.
allowed. Not allowed.
Right, so
It's
we just is that already clarified in the document?
I hope, but if it isn't,
Okay,
it must
so
be.
we should just call that out based on
It's
the
a classical
confusion.
request reply model.
Right.
So, well, but I must say that first, of course, in AKC needs, they agreed upon that ICE takes place by exchanging.
Yes,
Yes.
that's correct.
Notification. Yes.
So also, are we mandating that essentially the result of an ICE exchange is that we will always have new keys? That because you're mentioning that this is great for the
Well,
quantum
It is
resistant
well,
now.
not always. Well, as I said before, ICE is generic. Yes, in some cases, for example, I don't know. I can't come up with exact case. But for example, I must exchange some huge payload before ICE take place. I can use it, but this payload may not establish new keys. In this case, well, it is not updated of key seed. But for QSKE case, of course, if you exchange new key payload, we must use it.
Okay, so while I see that we're not required to get new keys here, I'm worried about the complexity, especially for the logic of one side saying, okay, I've done this ICE, and sometimes, depending on the content that happens to be in this, I need to get a new set of keys and redo that. Sometimes I don't. I think since our main case right now is that the point of this is getting new keying material, I would like to actually mandate that we always have to generate something new as part of this, because if you needed just some big packet, you could put that in auth today.
Well,
the whole point is that we're trying to protect the auth.
Well, I think that it must be in QSKE specification. So my suggestion, keep auth specification separate as a generic, and QSKE specification make use of it. And QSKE specification must say that when you exchange QSKE in auth, recalculate keys.
Okay, I agree that it should be general. I'm just concerned if we end up having code that says I'm doing aux and then has a code break to say sometimes I'll rekey, sometimes I won't, and that could be a source of bugs and issues in which sometimes we don't end up actually regenerating the keys. If both sides had that bug, we could think we did quantum safe, and we're not. Yeah, but in general, I really like this approach. So thank you for specifying this. I think it's definitely the right direction.
Don't go back to this previous slide, please. Michael Richardson. So I was really enthusiastic 2 slides ago or something about the generic ICE mechanism. And then this slide points out this discussion about rekey. And I begin to feel that it's not very generic. Okay?
Why?
Well, because of the rekey part, as we just said. So if we have to rekey after this,
well,
okay, if we have to rekey after this to make everything work, then it seems like we should just do a new ICE auth.
No.
Okay, there. So answer a question for me answer a question. There's a riddle there, right? Answer this question, please. So it's Friday. So assume that quantum crypto has broken Diffie-Hellman.
Oh, online. In real time.
Online.
In real time.
Yeah.
Well,
so we really need that the stuff that's gone bad. So the point is that means that first step is already null and void,
yes.
Right? So why bother doing this part in between? Let's just go to ICE auth, generate some keys, and then do a rekey with the quantum mechanism.
No. Well, first,
because once we get to ICE auth, we can do our fragmentation process.
Well,
in there, but
let me.
Well, but this is a fake auth.
No,
okay.
no.
It is a fake auth, right? So you haven't confirmed anything. So all you've done is added a state to a thing. We already have rekey, so you rekey with Diffie-Hellman, which was broken, we know, but at least it gives you somewhat a protection against random hobos who have no quantum computers.
Yes.
Okay. Then you do. I presume they're not going to be so.
Let me answer.
Okay?
Well,
but script kiddies today can do fragment attacks on your SA init, right? We know that. So now you have some not real, some protection, at least as much as ICE-auth gave you, and it's not a new state, and then you do a rekey with the quantum method.
Well,
to me, that just seems simpler. And as I said, I was really enthusiastic about it before, until we talked about this. And so I would say, if you can find a way to make it generic such that either the rekey always happens, or the rekey never happens, or we don't have to think about rekeys.
We are running out.
There
of
is
the
no
time now.
rekey. It's just a recalculation of SKE seed using the rekey formula.
That's a rekey.
Rekey formula.
Actually,
But there is no rekey exchange.
Yeah.
Well,
Actually, I think one of the things I would propose is to move this discussion onto the list, and also one of the things is actually SKE seed calculation should probably be moved to the quantum. So it wouldn't be upper here. It would be one of the results for the key exchange. Actually, QSKE calculation would be, by the way, after this we recalculate the SKE seed. But
Well,
Paul, you are taking the last comment.
Let me answer to Michael. Actually, if Diffie-Hellman, if not Diffie-Hellman, if IKC init key exchange is broken, can be broken online in real time, all bets are off. It's a bad thing. But I'm positive. I think that. Well, but anything. I think that we will end up with some post-quantum key exchange with rather small key exchange payload, so that it can be fit in IKC init eventually. I hope.
So, and just a clarification. So for if we hit rekey time and we want to use to create child assay exchange later on, then we're just assuming we can create a giant packet and fragment it, or what?
Once more, didn't understand what.
I'm just worried if we need something similar later on for create child assay. But I guess we can fragment.
It's create child assay.
Right. Yeah, I guess so.
Yes, create child assay. It's encrypted and it's so. Properties.
Can you
I will. Be
Can you quickly summarize this, maybe in a minute? Thank you.
In a minute. Yes, right. It seems that this approach is rather simple. It adds very minimal complexity to existing implementations. It's modular because iCalcs can be used not only for QSKE. It is not tied with QSKE. It's secure. Well, at least it is not. It is more secure than making fragmentation stuff and ended fragmentation stuff and encrypted IKC init. Next, please. Well, it adds reliability because we can make several iCalcs exchanges if you need to perform several QSKE algorithm, and making each message smaller that will benefit on lossy and congest networks. And what about performance? Well, it adds 1x round trip. That is that. But I think that it's affordable. So comments, questions, adoption.
I think we're going to have to take those to the list.
Yeah. Okay.
Thank you.
Thank you.
Paul, do you want to come up?
Paul.
Do we get more slides? Okay, next slide. Okay, so the history of this is not many people use labeled IPsec, but it's basically a way of transferring a security context from one machine to the other. And this is one feature we have currently in IETF1. And since I'm really hoping to write a draft called draft IETF1 die, I want to see like every feature that is left in IETF2. I want to be able to make sure that we can do this in IETF2 so that we can just tell everybody migrate to IETF2. So next. So this is currently how it looks like if you run this on a Linux kernel. You see there's just a standard SP entry, and it has a security context that I highlighted. So that's the information we want to basically transfer. So next slide. So this is my proposal. We give it actually it was more Tero's proposal again. We give it a traffic selector type. We reserve some bytes because the other traffic selector type that is not IP also did that, and it sort of makes it more similar. And then just the length, and then the length of the label. And then next slide. We still have. Do you want to comment on this first?
Yeah,
okay, sure.
I don't think it's is compatible with how IQ2 defines TS types, because traffic selector is composed of several TS.
TSI, TSR.
Yes, and all of them are treated as logical OR. For
Right.
example, yes. So if you add this one of TS type,
Yes.
it means that you filter by the security level, and you allow any IP address, any protocol. There's no filter on IP address and protocol. The right approach is to add two TS types. TS type IPv4 underscore sec label and IPv6 underscore sec label that will contain all the IP information and security label in addition, I think, because otherwise you have a logical problem. Well, for example, I include three TS selectors in TS payload. One IP address 10.1.1.1 something 0, another IP address 194 dot something 0, and the other security label is equal to, I understand.
Right.
So this selector allows IP packet with no security label to pass if it matches the first two selectors, because IP address is matched. So all traffic selectors in TS payload are treated as logical OR.
I see. Okay.
Yeah, that's one of the issues. Of course, there is there's also this issue that in IPsec in traffic selector we always have a range of those, so we can actually narrow them down, which is something that is very hard because this seems to be a string. So this is something that needs to be
So you can do that, right? So if the IC daemon is aware of what the security context means, it has some way of narrowing it down, because you can, however you express it in a string or an opaque blob of data, you can do narrowing.
Yeah, I mean, but the current narrowing code is always, this is the lower bound, this is upper bound. You can pick whatever range between those two. So this would be I mean, if you want
But
to use the generic narrowing code.
this is a more complicated narrowing,
Yes.
depending on how they define a security context. And I would
But
like to avoid defining.
I think this
how
is
it
something
works.
that we need to think about more about how to actually negotiate this, but it's something that we need
Sure.
to think about.
And let's take that thinking and discussion to the list.
Sure, that sounds good. Just if you forward.
Can we move on?
Yes.
Thank you.
Okay. Just forward the next slide briefly. So the only other issue that was kind of weird was if there's a zero size label, if it's null, what does that mean? Maybe that means any. And the other thing was that must the label always be the same for inbound to outbound? I can imagine that there might be use cases where that's not the case as well.
Okay. In the multi-level, Jared Oracle, the multi-level system users are very wary about information leaking.
Right.
So, so in this case, in that community, they're basically talking about label upgrade and downgrade,
right,
rather than narrowing. I think they kind of serve different purposes. I think for that community, the downgrade of label probably doesn't make sense if they actually want to talk.
Right. So then you need to use exact matching for the label.
Right.
Yeah.
Right. And that's
like it depends on if you say like if I have top sequence clearance, does it mean that I have secret clearance? Yes or no? Like for some that might apply, but for some that might not apply.
Right. But if I actually want a top secret channel, a connection, I probably don't want talk about or have secret traffic on.
Right. I agree. Yeah. So then you have to do an exact match.
Right. Yeah. And that your label looks like an example of a type enforcement label.
Right.
And in that case, it probably doesn't make sense to downgrade either.
Right. Yeah. That's fair. Yeah. I just picked this as the example.
If length is 0, my intuition is that maybe it should imply label isn't.
So it should
needed
any. Right. Yeah. It seems the easy way out, because we might want to say any anyway at some point, and so this seems the right candidate for any. Yeah.
Okay.
Thank you.
Brian. So this is one of the new items that everybody should have read this document, right? Because this is one of the important things, right?
Okay, so you can go to the next slide. So a little bit of background first. What on earth is this all about? So there was a time that when we were first looking at IPsec, and there was a lot of work on IPsec for unicast packets, which of course we all know and love. And there was a time saying, hey, you know, we have IP multicast as well, and there's a different security problem for that. So this multicast security group spent some years looking at defining the problem, some architecture documents. That resulted in some extensions to the IPsec architecture, and then a key management method called the group domain of interpretation, because you'll remember that ISACAMP had DOIs, and that's an IPv1 protocol. So in the whole spirit of IPv1 die, we're presenting this draft. You can go on to the next slide. So to remind you how IP multicast works, there's at least one sender, could be many, and you've probably got a small to a large number of receivers. And the point of IP multicast is to take advantage of the multicast replication of that packet. So you've got a video frame or something that you want to send out to hundreds or thousands of receivers. You'd like to use the network to actually do the replication. There's a number of multicast routing protocols you might remember about that cause that to happen. But the net effect, of course, is that now you have to have a sender with a transmit SA that matches a receiver SA on lots of different devices, so you can't use IPv2 to set that up. And so that's what this is really all about. How can we set up those IPsec SAs? There's two kinds of protocols that are defined. Something we call a registration protocol, which allows a group member to authenticate to a group controller key server. And after authentication is authorized, yes, you're part of that group. And then if that's successful, there's some group policy and keying material that is downloaded. And we'll talk about that in the next slides. And then there's a rekey protocol, which is what you'd expect. And we'll talk about that later. Next. So we have two registration protocols defined, very much like you have ICAuth and create child SA. We have something called GSA auth, which is very much like an ICAuth, except we're passing some new types of payloads. There's an ID payload that the group member sends, which says, this is the group I want to join. And that's otherwise just a normal ID payload. And the important ones coming back are the GSA and the KD payloads, where GSA would have a set of policy in it. So there'd be some IPsec transforms and some other policy. And then the KD has the keying material that goes with that. The initiator may also send an SA group, which is just an SA payload, and that may inform the GCKS. Here's the policy I can handle. Here's the algorithms and transforms and such. And that would be advisory for the group controller key server, but there's some cases where that might be useful. And he may also send a notify. We'll talk about that later. And the key server may also return some delete payloads for some previously distributed SAs. GSA registration is equivalent to the create child SA. It's exactly the same otherwise. Next slide, please. Rekeys. So there's two kinds of rekeys. Let's do the second one first. The GSA in-band rekey. If you have left up your registration ICSAs, the key server can use this protocol to do a rekey by pushing exactly the same information down to the group members. If you do not have that, then and you may not wish for a large group, for example, to maintain the ICSAs, hundreds or thousands of them to the GCKS. Then there's a separate protocol that sends the same information down in a IPv2 payload, but this is a different SA. Okay, next slide. So we'll just drill down a little bit into these payloads. A GSA payload has, in the MSEC terminology, a tech policy and possibly a KEK policy, and then maybe some other stuff. The tech policy just means here's what you must install if you're in IPsec if you're going to participate in decrypting and looking at these packets. So there is a spy sent down, some traffic selectors, and a single set of transforms because there's no negotiation here. The key server is declaring what you shall do. if you want to read this traffic. A QSKE policy would be if there's a separate rekey essay that we talked about a minute ago. So there's an IK header spy, some traffic selectors, and then some attributes about what are the transforms that are protecting this and so on. And that would produce new text and possibly a new QSKE if you need to reconfigure that. We'll also talk about another use for this in a minute. The GAP is just a general payload that might be effective for the whole group, including, for example, giving some synchronization times to, say, switching from an old set of essays to a new set of essays. Because, of course, you want the whole group to do that at about the same time. Okay, next slide. So KD is providing keys, as we mentioned, for these other things. So there's the tech. Again, we have the spy, so we can match them up, and then we have the key material that matches the transforms that were sent in the registration. Same thing for the QSKE. These last two are kind of interesting. The QSKE would be used if you're downloading a single key. I mean, you're maintaining a single key on the GCKS, which group members will use to decrypt and authenticate the rekeys. But one attribute of large groups is that you may need to deauthorize one or more group members from time to time. And you don't want to affect the entire group. You don't want to tell the entire group to come back and re-register and disrupt traffic for a period of time. So there are a set of algorithms that the research community arrived upon. The one that we have in this draft is called LKH, or Logical Key Hierarchy. It's actually defined in, I think it's RFC 2627. And there's also an appendix in our draft that shows how that works. So in that case, the key server does maintain this key tree. You can think of it as a very large, kind of a binary tree. And at the very bottom of that tree, all group members have a secret key they share with the GCKS. And then there's these logical keys in between. And when a group member registers, you essentially give them the path of the keys from the root, which is the QSKE, all the way down to themselves. And then when you want to rekey, you can send out a multicast message to everyone with a few of these key vectors in them that effectively give everybody the context to rekey except for the member you're deauthorizing. It's nice because you can do this in the multicast rekey. Everybody else gets the new rekey, which then you can send new texts out, and your deauthorized member can all of a sudden no longer have the what he needs to decrypt and view the content. The SID is solves another problem. If you chose a counter mode algorithm, you have to be, and you have multiple senders, you have to be very careful about the nonces, of course. So there is an RFC that David McGrew and I published some years ago that describes a method of how you can take some bits in the nonce and call that a sender ID, and you make sure that you give us this sender ID to only one group member ever within a set of essays. And as long as you give every group member a different SID, every sender a new SID, different SID, you will have maintained individual nonces. Okay, next slide. We mentioned some of the reused payloads, ID, standard ID. Most of the time you use a key ID to say this is a number of the group I'd like to join, but it's also valuable to be able to say, hey, I'd like to join this IP multicast address group. And the SAG is a standard SA payload. Standard delete payload. You may have to delete things that you've told them earlier. And next slide, please. It's the last one, I think. Nearly notifies. There's some new notifies that come along with this. Hey, you tried to join this group and we couldn't authorize you, or hey, I don't know about the group that you asked me about. Or the last one is a way for the group member to say, I need more than one of these sender IDs. Maybe he's got multiple crypto engines that are going to be using this, or he's really, really fast sender and he's going to run out of nonce space and you need some more. Okay, last slide, I think. Next, we have this draft has been ongoing for some time, and we're just coming now actually to have it to have it actually published. We have one full implementation. There are some partial ones. I think Valerie might have a small one. Tobias has a couple actually of students that have worked on this interoperability. You might remember a couple of IETFs ago, he demonstrated a minimal group IKV2 client, and now more recently he has a key server that's, I think, based on, it's OpenSwan, right? And that's the paper that he tells about his interop experience, and we'll be doing more interop on this. So this is, I believe, a new area. So
yeah. So I have one question for you. First of all, is that if I understand correctly, the current text is so that we are actually running on different port, right? Port number. So we are not running on port.
Runs on 848 today. Or at least that's the one that's recommended.
That's actually one of the questions we actually want to decide if we actually want to integrate it more, because I guess one of the things might be, but well, it was still as a separate MCAST. I was thinking about it might be better to have a separate, but if we are now taking it here, it might actually be better to even more harmonize it to use it. And this would actually mean that one of the things would, for example, do so that in IKE out, so not use GSA out, use IKE out with this childless essay, and then because that would be exactly the same. And then do the child essay creation as a separate with the new registration, which would actually solve.
So you're saying always do the IKE essay. I mean,
always
do IKE auth and then always follow it with the registration.
Because that would actually allow you to do use the quantum method we were talking about. So because the first two steps will be always same. Yeah. That's actually my question. Is that something that would be willing to think about?
Well, certainly if you're in port 500, you could do that. We might want to also use 848 and then maybe you wouldn't have that same restriction. Yeah.
Right.
We might even want to, harmonize terminology and call them IKE keys and IPSEC keys rather than KEK and TEC.
That's probably a good idea.
Yeah. So I've got, one question, one comment. I know that the previous standard, the GDOI, was used, at least in Cisco, for things that are not multicast. For unicast, is the plan to continue with that or leave it out of the IETF?
So the policy that you download could be unicast or multicast. Sometimes it's used for a mix. You're right. This is intended. I mean, we're presenting this as being intended for multicast, particularly large multicast groups. I mean, I wouldn't want to say you can't do the other, but that's not the point here.
Okay, and one comment that CFRG now have a document for some variation of ASGCM that does not require sender ID because you can just generate the. It's not so catastrophical to reuse the nonce, and the nonces are slightly bigger, so that might be interesting for this algorithm, for this protocol.
Right. So I would say that if that gets, if there's an IPsec transform that would get developed with that, of course it would fit right in. That'd be perfect.
Yeah, the disadvantage with that particular transform is it tends to be rather more expensive than the regular GCM.
Just want to.
The number that were quoted in CFRG were about 10% penalty for using that, which are sort of okay.
Okay, so I'd like to see a show of hands for those that have read this draft.
Any version of that.
So few. I think it would be useful to actually get a little bit more review before we consider it as a working group item. So if you could post to the list asking for that review, that would be appreciated.
Very well.
Thank you.
And if people who have read it and had comments now actually harmonizing and this kind of thing, actually would be a good idea to get the comments out. So next is then the essay in it, privacy concerns.
Thanks. Good afternoon, everyone. I'll try to be quick because we're running low on time. So my name is David Skenazy. I work at Apple and, amongst other things, on our IKV2 stack. I'm going to talk about privacy aspects to IKV2. Next slide, please. IKE is really robust. Like, we've done it, or not we. This working group has done a great job before I even showed up. The one aspect, though, that is a growing concern that maybe wasn't at the time is privacy of the users, and in some cases, privacy of the servers. So two things that I think we should be able to secure. One is the identity of the initiator, and the other is that the fact of a server is running. I'm going to go into more detail explaining why. But one thing that I really want to insist on is this is meant as an addition to what we already have, not as a replacement in any way. We don't change the auth payload. That's still there because we still need it for the properties it gives us. Next slide, please. So the identity of the initiator, as you know, it's sent encrypted, but because in IETF2 the burden of identification is on the initiator needs to send its identity before it has authenticated the responder. Next slide, please. Which means that if you have an evil on-path man-in-the-middle attacker, they can intercept your SA init. You end up doing Diffie-Hellman with them, and so you end up sending your identity to that interceptor instead of to the person you're trying to reach. That in cases where if you're roaming on some Wi-Fi network and someone controls the access point, they can figure out, and you're trying to use IETF2 to protect your privacy, they could use this to know who you are, which really isn't great. Next slide, please. Another aspect is the hidden server. Thanks to the TCP encapsulation RFC, we now have a way of running IETF2 over TCP, but also over TLS. And one use case I see for this is running it on TLS on port 443 on my own server. So to anyone, it looks like I'm just running my own website. It's great. There's even a photo of me on it. But I can connect to that and actually have VPN services without anyone knowing about it. The problem with that today, so that the way you would do that is you have some code that's between TLS and HTTP, and if the first bytes of the new unencrypted, well, the abstract unencrypted stream, once you've decrypted TLS, if it starts with IKTCP, you know it's going to be an IETF2 connection. You can hand it off to your IETF2 daemon. Otherwise, you just hand it off to the HTTP parsing code. The problem there is if anyone sends me an SA init, I'm going to reply with an SA init. So they can find out that a server is running. And the reason this matters is if the network operator is probing places to find out, is trying to actively block VPN, the first thing they're going to do is block UDP, but then they could also be probing to see if you're running the server or not. So we want to hide that fact. And simply responding with an SA init is a clear indication that, yes, I understand IKE and what this means. So we want to make sure that to someone who's not authentic, who doesn't have any keying material, it just looks like the invalid message or just shutting down the connection that any server would do if you send something that doesn't look like it's valid HTTP. Next slide, please. So how can we solve this? The solution is very simple. You add an extra shared secret to the configuration. So it's separate from the one used to authenticate. And when you configure your client on top of all the keying material, you also give the shared secret and a PRF. So you don't need to negotiate that. That's just part of the config. And what we do is we add a notify to the SA init messages. We do an HMAC with this shared secret. So you kind of have some proof that you know you are who you say you are. Next slide, please. What this looks like is the initiator sends this as an extra notifier on every message he sends, and on every IKE SA init, and the responder can choose to verify this and silently drop it if that fails. So that allows us to hide if the responder is running from people who don't have this shared secret. The responder, when it sends this IKE SA init reply, sends a code with again, an HMAC, so the initiator knows that that person also has the shared secret, so it's safe to give them your identity. If the initiator receives something and it's not good, it just fails the exchange. Question? Or
I have some questions, but I think I just so this is protecting to make sure that the IKE responder is not visible to the nefarious network operator. Is that right?
yes. Well, there are two separate problems. One is the identity of the initiator, and one is the secret server. They're completely separate, but it just so happens that this simple solution works for both. But you could imagine only configuring one half of that. Next slide, please.
Can we hold on clarifying questions till the end?
Yeah.
Thank you.
Yeah. Yep. Yeah, I'm almost done. I'm almost done. So how we compute it? It's a simple HMAC. We add a string in there in case people reuse the same key, because you never should, but people do it anyway. And then the only thing that we MAC is on the first one, the initiator nonce, and on the second one, both nonces. So that allows us, especially on the second one, you know that the server actually really has their shared secret, but because they just HMAC a nonce, you sent them. Then your nonce needs to be big enough for the security IKV2 anyway. On the first one, all your macking is something you're sending. So you could, this is, and actually next slide, completely vulnerable to a replay attack for the init one. That said, that's been true of all, I guess, init requests, and we're not trying to solve that. The reason it's okay here is the scenario where you want to validate the SA init of the initiator is the hidden server one. And in that example, when you're running over TLS, you know you don't have an on-path attacker because your path is a TLS connection to your server, which you can validate the cert of the server to know that that's not there. So if someone comes in, they'll be off-path in a separate TLS session. And that's it. Questions?
Michael Richardson. So the whole extra PSK smells like IKV1 group PSK stuff with XAuth, and so I kind of feel unhappy about that. So I guess you're in a scenario where you are able to provision these PSKs easily to clients because you've provisioned something else, which makes me wonder why you wouldn't just provision raw public keys or something. And I would be happier if the thing that you provisioned at both ends was a raw public key rather than a PSK. Maybe the quantum guys would disagree with me, but for that. The second thing I want to ask is, since in the cases that you're in a TLS connection, that you've actually validated the cert of the server, okay, it seems that you already have a public key that the server can sign with to prove that it's really who he says it was. And so, or in fact, that's not even an issue because the connection's already, you've already done that. Right. So they want to do that. Yeah. But the point is, I'm trying to say, it seems you've already got something in some cases from the other side. So anyway, I'm not happy about more PSKs anywhere in the protocol. And I think that raw public keys are as good as PSKs every time.
So one of the things I was considering for this is, instead of having it like specified as an HMAC, we could have it as something more generic, kind of like the way the auth payload is defined today, of you use any of these options and we open it up to anything that can be used for auth. That would be okay to me.
So they're giving it. I have some. If you go one slide back, there's one problem here is two. That one. The problem there is that when the responder is verifying the first one, let's say I have 1 million customers, I have 1 million initiator sectors, and the only way to verify this is to go through all of them, which allows very easy denial of service attacks. This was the problem with the first quantum, problem. So that's one of the issues.
No.
Yes, that's actually the group key.
Actually, this isn't that insane in this case, because
I know,
this is just for privacy. Remember?
Yes, but yes, but anyway. So if but anyway, there's two problems here, and I agree. The first one, the one that I withheld the identity, I think that's more important one, and I think we should solve that in different ways, because there's a way that we actually discussed. In the quantum discussion, we were having we do pseudonyms. So instead of using our own real identity in auth, we use pseudonym. This is completely random identity we get. We know it beforehand. We use that one. Server goes to this random identity, maps it to real user, and finds my information. And then after we have finished the authentication, we do extra exchange saying, okay, by the way, your next pseudonym is going to be this new random string. And this kind of, and we can have a more complicated, we can have a list of these, or we're gonna have a hash chain of those. So these are, but this actually will solve the identity issue, and I think that's a better way to do it. This hidden server code is something that is, first of all, I think the common usage in IETF is that we are not trying to bypass all of the policies set by the administrator. So, trying to get past all of this, blocking of the firewalls is something that we usually don't try to do that much. And I mean, it's always going to be a little bit, from the traffic analysis, it's quite often very easy to see that this is not an HTTP or TLS connection to the server, or if it's a TLS connection, it's a TLS VPN. Because you have a sending packet and you get the reply ACK and you get the TCP packets, you get ACK and then the silence. And I mean, it's very easy to see that this is traffic, that is VPN type of traffic. Is it an IPsec VPN or if it's a TLS VPN? Who cares?
Fair enough.
Can we make these short?
Yeah.
Thank you.
Valery Smyslov, response. So I see first scalability problem with this approach, then algorithm agility problem, because PRF is fixed, well, the box tied. It's difficult for you to change PRF because you need to change configuration on all these devices. So it's again scalability problem. And the next problem is that you mentioned is no replay protection. So I think that if attacker can use the first packet, it can replay with it and get all the validated information. They are trying to find the guest. So you're not solving your problem.
Well, wait, no, the replaying the SA init allows you to find a hidden server.
Yeah, sure.
And in that case, if you're using TLS, you can prevent the replay attack. The SA init of the responder, that you can't replay because it includes the initiator nonce.
Tommy Polly. I think Tira's points that those points are very good about the hidden server ones. I think especially in that case, since you're relying on this TLS connection already to prevent the replay attacks, you could have client authentication in TLS and just solve this anyway.
That's visible in the clear, as in the fact that you're using client authentication is visible.
I think, right. There's also going to be lots of problems getting this through any sort of review because IETF doesn't really like hiding things behind this. I think if we focus on the privacy of the IDI in a draft, like we could eventually tackle these separately, but I think that one is a much clearer case, which we have other options for, and we should tackle that because that is a really clear attack vector on users. And I would suggest like separating these out and continuing to work on the initiator privacy.
Last comment.
Well, so Daniel Migo, Ericsson. I think, yeah, it's an interesting topic that, well, it might not be the solution, but I agree with mostly repeating what Tommy said. Maybe splitting the two problems into two different issues to solve and continue the discussions to see how we should best address this, at least the privacy of the ID. But I think that's work that should be going on in this working group.
Thank you.
Thank you, everyone.
Unfortunately, we're almost out of time. There is time to at least come up and introduce the dynamic IPsec PMTU draft and maybe direct the working group as to what you would like them to do after this meeting. Maybe a minute or two.
Okay. Ron Bonica, Juniper Networks. There's no time, well, probably no time to introduce the whole draft or run through the whole presentation, so I'll at least introduce the problem. An IPsec tunnel, like any other tunnel, has a PMTU, and somehow the ingress needs to know what that is. One option is to say, the PMTU for IPv6 is 1280, you never get to go any higher. The other is to do some kind of PMTU discovery. Unfortunately, PMTU discovery relies on ICMP messages, which can't be trusted. So, in the transport area, there is a draft referenced in the document that talks about a way to send messages in band to discover the PMTU. Thank you. We have decided that that's a good idea. The draft in the transport area gives you 3 degrees of freedom. What does your probe look like? In this case, the probe is a message of various lengths to discover the PMTU. It goes inside the IPsec tunnel, so it's encrypted. There's a response that gives you an idea of what the PMTU actually is. Oh, no, it doesn't give you that. What it does is either acknowledges or doesn't acknowledge your probe. If it got through, your probe was less than the PMTU. If it didn't get through, your probe was greater than the PMTU. And the 3rd degree of freedom is, what do you do to validate ICMP messages? In our case, we don't trust any of them because we're security people. Even on days when we've taken our meds, we don't trust ICMP. In any event, what I'd like you all to do is take a look at the draft, send comments. It's very, version 1 is very different from version 2. In fact, it's totally different. And if the comments look good, we'd like to adopt it as a working group draft.
Great. Thank you.
Okay, thanks.
And with that, I think we're ready to conclude the meeting. So good luck to everyone, and we're done for the week. Thank you. If you haven't signed the blue sheets, please come up here and do so. Yes, thank you so much. I borrowed her power adapter.